first step is to be able to visually determine what is an aldehyde and what is a ketone. Aldehydes have a hydrogen atom attached to the carbon-oxygen double bond, whereas a ketone has a hydrocarbon, for example, CH3 or CH2CH3, attached to the carbon-oxygen double bond. Because of the hydrogen in aldehydes, they are easy to oxidize. Ketones do not have a hydrogen attached to the carbon-oxygen double bond, so they aren't easy to oxidize. Because of this property, we can easily distinguish between the two chemically using oxidizing agents. We know that primary alcohols are oxidized to aldehydes, which can be further oxidized to carboxylic acids. Secondary alcohols are oxidized to ketones, which cannot react any further, and tertiary alcohols cannot be oxidized at all. This is because the hydrogen is attached to the carbon-oxygen bond. In a primary alcohol, there is the carbon with the alcohol group attached. It also has two hydrogens and a carbon bound. We know to be easily oxidized there must be a hydrogen attached to the carbon-oxygen bond. The primary alcohol reacts two hydrogens with an oxidizing agent, which forms a carbon-oxygen double bond. The aldehyde that is formed still has one hydrogen attached to the carbon, which means it can be further oxidized to a carboxylic acid. A secondary alcohol has the carbon bound to the alcohol group, as well as two carbons and one hydrogen. The secondary alcohol is oxidized to form a ketone. This ketone cannot be further oxidized, as there is no hydrogens attached to the carbon-oxygen bond. Tertiary alcohols cannot be oxidized at all, as they don't have any hydrogens attached to the carbon, which is bound to the alcohol group. Here we're mixing acetone and Tollens reagent. Tollens reagent is an oxidizing agent. This means that if there is a color change or chemical reaction, the aldehyde is being oxidized. We then add equal amounts of formaldehyde or methanol and Tollens reagent. You can immediately see a color change. To speed up the reaction, both test tubes are placed in a water bath. You'll begin to see that the test tube with acetone does not have any change, whereas the test tube with formaldehyde creates a silver mirror on the glassware. We know that for a positive Tollens test, a silver mirror will appear. This means that the test tube with formaldehyde has a positive test, showing that the formaldehyde has been oxidized to its corresponding carboxylic acid, whereas the ketone has not been oxidized. Looking at the half equations, we can see that Ag plus has gone to Ag. This is the silver that we get on the glassware. First, place 4 ml of Benedict's reagent and 1 ml of acetone in a test tube. Then, place 4 ml of Benedict's reagent and 1 ml of formaldehyde in a test tube. Then, place both test tubes in a water bath. The water bath speeds up the reaction. Benedict's solution is also an oxidizing reagent. A positive test means that the copper in the Benedict solution has been reduced from Cu2+ to Cu+. Distinguishing between the ketone and the aldehyde is that the ketone has no change in the blue color, whereas the aldehyde goes from a blue solution, producing a dark red precipitate. However, with formaldehyde, it is such a strong reducing agent that the reaction goes beyond Cu+. As you can see on the test tube, the copper has formed a solid, as in the Tollens reagent formed a silver solid. This shows that the aldehyde has been oxidized and the copper has been reduced from Cu2+ to Cu. Comparing the two test tubes, we can see that the aldehyde has been oxidized, whereas the ketone has not. From the half equations, we see that copper 2+ went to copper plus, then copper, which is the solid seen on the glassware. The aldehyde went to its corresponding carboxylic acid, then to carbon dioxide. To make Tollens reagent, add silver nitrate, sodium hydroxide, and 3 molar ammonia. Add 2 milliliters of 0.3 moles silver nitrate and then 1 to 2 drops of 0.2 moles sodium hydroxide. A brown precipitate will form. Then add 3 molar ammonia dropwise until the precipitate has dissolved. It is important not to add excess ammonia. All monosaccharides are reducing sugars because all monosaccharides have an aldehyde group. Glucose is a monosaccharide. Therefore, when glucose is mixed with Tollens reagent, a silver mirror should form. This is because glucose has an aldehyde which can be oxidized to a carboxylic acid, which means that the silver in Tollens reagent can be reduced from Ag plus to Ag. You can see that the silver mirror is forming on the glassware already. The half equations show that glucose is oxidized to a carboxylic acid, and Ag plus is reduced to Ag. Benedict's reagent is an oxidizing reagent, and glucose is a reducing sugar. Place 4 milliliters of Benedict's reagent and 1 milliliter of glucose in a test tube and place in a water bath to speed up the reaction. We can see from the half equations that glucose is being oxidized to its corresponding carboxylic acid, and copper 2 plus is being reduced to its corresponding Cu plus. We can see in the test tube that the colour change is starting to happen. The blue has gone to a red precipitate, which is the Cu plus. This time we mix Tollens reagent and apple juice. This will clarify whether there are any reducing sugars in the apple juice. The label says there is sucrose. Sucrose is a non-reducing sugar, therefore we shouldn't see a colour change. However, immediately we see a dark black precipitate forming. This is common of a silver precipitate. However, there's no silver mirror present. There must be other chemicals reacting to prevent the silver mirror from forming. This time we're mixing Benedict's reagent and apple juice. This test will tell us not only whether there is reducing sugar present, but also the percentage of reducing sugar in our solution. Immediately when adding the two reagents together, we see a colour change from a light blue to a turquoise. We speed up the reaction by placing this in a water bath. Over time you see that the solution will go to a dark black, followed by a red solution. This shows that the copper is being reduced from copper 2 plus to copper plus. This shows there is a reducing sugar present in our apple juice. Comparing it to the chart above, we conclude that the apple juice has more than 4% sugar.